Okay, this is the very first of the real lectures for Earth and Life history. And so I want you to go ahead and start by looking in your textbook in Chapter 1, and in particular the pages 6 through 9 introduce us to the concept of deep time. I mentioned before that time in geology isn't just in days, hours, years, decades, or even hundreds of years. We talk about millions to billions of years. So, a few first concepts to get into that. And right off the top, we have this idea of what we call uniformitarianism. The guy in the picture is James Hutton, and he's a very, very, very famous geologist from the 1700s. And he came up with this notion of uniformitarianism. See in the notes there it says equals uniformity. That's how I will write something when I know that there's another term for the exact same thing. And so I'll bounce back and forth between the two. They mean exactly the same thing. And what they mean is simply that the present is the key to the past. If you want to study ancient rivers, ancient oceans, ancient anything, you need to know the present. And so one way to look at this is to say that the processes that we observe today, the weather, rivers flowing, waves crashing on an ocean, an earthquake happening, they have always operated in geologic time. So let's look at a quick example of this. So for the present, we have sands that are forming today at a beach. So the lower picture there is a beautiful beach. You probably all wish you were there instead of here, wherever you're at listening to this. But, a beach. We all understand what a beach is, and there's the sand that's forming at the beach. The upper picture is just sort of a pinch of sand between a couple of fingers, and then it's magnified under a microscope, and, sand. So we know how it forms. It's at a beach. Waves are crashing. It makes a product that we call sand that looks like that. Well, if we look at ancient rocks, so not a modern beach, if you look at the lower picture there, there's a cliff, and this cliff is from Mexico, and it's about 14 million years old. And if you were to go up and sample the rocks from that cliff, then you'd get a block like the one in the upper picture, and it is sandstone. So if I looked at it under the microscope, it is sand, little sand grains. They would look very much like the sand grains in the previous picture, but these are a million years old. And so if I want to know how this rock formed, my best guess is to look at the modern example of the thing. So the present is the key to this past. All right, let's talk a little bit more about rocks. Every geology textbook anywhere has a similar figure to this. I just ganked one from another textbook, different from yours, just to show you it's all the same. And it has the three major rock types that we have on planet Earth: sedimentary, igneous, and metamorphic. Well, I'm going to talk about a couple of them real quick. I'm going to dismiss one completely. And then, as you can see there, I've made sedimentary in red. Those are going to be the key ones for us. So, igneous rocks, first of all. They are rocks that are made by melting and cooling. Rocks get heated so hot, they literally melt and become a liquid. And then when they cool down, they become a solid again. And my analogy, I always tell people, think about a candle. You light a candle, the candle wax melts. It has that pool of hot wax there. But if you blow out the candle, it hardens up again. All of the little arrows that you see on this diagram, notice that the arrows go from igneous rocks to metamorphic, metamorphic to igneous, igneous wrapped around back to igneous. That means that any one of these three rock types can be turned back into another one. So for igneous rocks, if you melt anything on here, it becomes an igneous rock after it melts and then cools. Okay. Metamorphic rocks. Go ahead and put a big fat X through those, because these are rocks made by very, very high heat and pressure. And in fact, the pressure is so high that it typically destroys the evidence that we want to look at to study geologic time. Mostly, I'm talking about fossils. So for me as a paleontologist, seeing metamorphic rocks literally means Rex, turn around, there's nothing for you here. So I don't test you on it. Go ahead and exit off. And then finally, sedimentary rocks. These are going to be the most important ones. But before we get there, I do want to talk a little bit about igneous rocks, just so you know the basics. All right. We describe igneous rocks by what we call their texture. And texture for igneous rocks, it isn't, most of you think of texture and you think of how does it feel, like the texture of this shirt, the texture of this table surface, whatever. It's not that. Texture for igneous rocks literally means, can you see the individual crystals? The rock you're looking at in this picture is about as big as a baseball, and every one of the different little colored specks on here, notice there's black specks and sort of orangey specks and white specks and gray specks. Every one of those is an individual crystal. Now these crystals grew by cooling, just like I said with the candle cooling, very, very slowly and deep within the earth. So below our feet right now, there are rocks like this cooling, but it's many, many miles below our feet. And so these things have very little interaction with life on Earth. If you see an igneous rock like this, it formed an environment that had no life in it. So it might be exposed at the surface today because of geologic processes, but it occurred first deep, deep, deep within the Earth. And the classic example, e.g. example given, is granite. That's the state rock of Wisconsin, and there's a picture of one of these things. The next slide just shows a cartoon of where all the different places igneous rocks can form. The upper part there is the surface, but all of that bright orange stuff that you see going down deep within the earth, that is going to be this igneous material that hasn't cooled yet. It's so hot it's still a liquid, so we call that magma. And you can see all the different shapes and ways in which it's kind of parsed out through the earth. I'm not going to make you memorize or know that for this class, but realize that if it is down there deep within the earth, it is cooling so slowly that those little crystals, they start out, so small you can't see them even with a microscope. They start growing and growing and growing until they become what we call phaneritic texture, meaning I can just look at it with my eyes and I can see the crystals. So phaneritic rocks are everything that would form within the earth. Well, notice at the top here, here's a volcano, and we know that volcanoes are places where some of this hot molten material can make it to the surface. As soon as it shoots out onto the surface, it's a little different. It has a different texture, and it indicates a different type of igneous environment. This we call aphanitic texture. If you look at this rock closely, you can't see individual crystals on it. It's just a big black mass. There's some color differences and cracks and breaks, but here the crystals cooled quickly. So quickly that they didn't have time to grow big. And that's what happens. That's what happens when this hot magma comes to the surface. The surface of the earth is cold. It's so cold that this lava, this magma comes out, it becomes lava, it cools really fast. The big difference is, so if you see crystals, it's phaneritic texture. It formed below us on the earth. If you cannot see crystals, it is aphanitic, and it formed at the surface. Since it formed at the surface, this potentially has major effects on life. And so this is potentially important for us. Think about it. If you live near a volcano like this, say you had a house just next to this thing here, well then the hot magma that comes out and becomes lava, it can affect you. And so this slide, it's very crude, simple cartoon, but it shows you there's the magma, and as it comes out on the surface, it's lava. Down here, everything below in the earth would have phaneritic texture, but as soon as it bloops out, it's aphanitic. Now, people ask about the time difference. Some of this magma down here is sitting here cooling for millions of years, and usually it is at least thousands of years, whereas if it shoots out on the surface, it cools in a matter of hours, days, weeks, months at the longest. Here's a picture right here of an active lava flow sort of cruising through a forest in Hawaii. You can see the black stuff here is the lava. The reddish orange stuff is the hot molten part. It's still liquid, but it's cooling. And when it cools, it becomes this black mass. It is advancing towards this forest. And if you look closely, you can see the forest is incinerating. The smoke is coming up, and it is going up in flames. So this igneous rock is having a major effect on this life right here. Now, a bird in this tree, it can fly away, go away somewhere else. The trees, they've got no choice. They're incinerated. Think about all the little earthworms and bugs and little critters that can't really move fast or far. Life also affects them, or they're also affected by this. Another example. Here is a trailer park in Washington state, and the mountains that are sitting here above, if I'm a geologist, I park my car, I walk over here, and if I were to sample this, I would see that they all have aphanitic texture, meaning this is igneous rock that came out of a volcano and cooled very quickly. But look at this. There are thousands of feet of thickness here. This is an example of not just a small volcano having a small effect locally, killing trees locally, but big time. If we look at it on the map of the United States, it's this irregular polygon over here in Washington, Oregon, a little bit of California, Nevada, and Idaho, a couple places here, and we call this the Columbia Plateau. And again, it's an example of just rocks that a few million years ago erupted and covered huge portions of the United States here. And this had tremendous effects on life in this area, but we have evidence from fossils that even farther out this had effect. So igneous rocks, they are not entirely important for this class, but I wanted you to get this designation, the separation between rocks, igneous rocks forming within the earth and forming on the surface of the earth, and the fact that they are sometimes very important for life on earth.